Hello everyone, welcome back. So this time we're actually going to try an example of calculating the moment of inertia. Okay, we're going to do around both the x and y axis. We're going to try to follow the steps from earlier. So as usual, I'm going to stop here, pause, give you a few seconds to try to work on it on your own. So 3, 2, 1, and we're back. So let's get to it. Oh, there we go. So what is our solution? Well, if I'm going to do it around the x-axis, I choose an element that is parallel to that axis, so a horizontal element. And I need to figure out what the height of this is going to be. Well, it's going to be 1 minus x, because x is usually measured from this axis right here. So that'll be the height, and then the width, and then the height would be simply dy. So that's my differential element a right here. Now I see that y cubed is equal to x squared, so if I want to, I can solve for x in terms of y. Now I simply take a square root of x, which means y to the 3 half is equal to x. So 1 minus y to the 3 half dy. When around the x-axis, I just simply take the integral from 0 to 1 of y squared times all of this. And while this isn't the best integral in the world, it's not terribly difficult. No very difficult rules here. And I'll get 0.111 meters to the 4th. Okay. Now how about around the y-axis? Well, going around the y-axis, it's a vertical axis, so I want a vertical element. So it's going to have a width of dx. What's its height going to be? Well, its height is going to be equal to the height of this line. So x squared dA, well, the height is going to be y, which I don't have a term for yet, so x squared y dx. Y dx is the term dA. And then I'm going to solve for y in terms of x. So I take the third root of y and the third root of x squared, and I get x to the 2/3. So that's all nice and simple. 0 to 1 of x to the 8/3 dx. I plug it in, and I'm done. 0.273 meters to the 4th. You're like, wow, that was super easy. This one was pretty easy. And the steps, as long as you follow them, are pretty easy. The integrals are also usually not terrible. If you see a terrible integral, it usually means that you've made a mistake in how you're setting it up. So rethink it. Go back and try it again. I think that's everything. Yes. We could have also used a vertical strip if we wanted to. There's lots of ways to do it. We could have used a vertical strip if we wanted to. And how would we have done that? Well, if I use this same strip, but this time for the moment around the x-axis, I would still have y squared dA as my integral. And then my dA would be equal to, well, what is the height of this box? It is simply y times dx. Okay, so I can do that. Y squared dA, y times dx, I put in here. And then I have to solve in terms of x. Well, it looks like for us, y cubed, x squared, we're all good there. If you wonder where this 1/3 comes from, just leave it for now. You can ignore that for the moment. Just know it will come back in our section 10.2. Fairly soon, this is just jumping ahead to show you the parallel axis theorem. So don't worry about this one for now. My advice is always choose an element that is parallel to your axis. It makes things a lot simpler. Okay, with that, we're done, and we'll go on to a little bit harder problem next time. Hope you enjoyed this. I'll see you all next time. Bye-bye.